Okay, we will start with the second part of the course, namely transfer phenomena, which in itself is split into three parts, namely momentum transport, energy transport and mass transport. And what we are going to discuss now is momentum transport. Fluid flows can be analyzed either through fluid mechanics or momentum transport. And what we are going to discuss in this lecture is the equivalence between these two approaches and what is subtle difference between them. So, to be more specific, we should say we are going to discuss this double headed arrow which says both are equivalent. Okay. Let us look at the outline. So, as usual you will understand this outline better at the end of the lecture. So, to begin with, what we are going to see is two different interpretation of tau. So far we have been looking at as a viscous stress. Now we are going to view in a different viewpoint, namely as a molecular momentum flux, something like duality of tau, just like we have duality of light. Then we are going to look at equivalence of fluid mechanics and momentum transport, and of course discuss the subtle differences between them as well. And then we are going to rederive the linear momentum balance and the Navier-Stokes equation following the momentum transport approach. Okay. That is the overall broad outline. Let us proceed and then you will understand this with more clarity. Okay. Let us start with our well known example. So, just a recall. We will start with a planar cuvette flow between two parallel plates and the top plate is set in motion. So, let us quickly recall flow between two parallel plates, bottom plate is stationary, top plate moves at a constant velocity V p. We have derived the velocity profile using the Navier-Stokes equation. Now, we need not assume this profile. We derived the velocity profile to be linear given by V x is equal to V p by h into y. Now, the shear stress tau y x is equal to mu dou V x by dou y for this case, or we can take it as one dimensional Newton's law of viscosity. So, if you differentiate the velocity profile you get V p by h. So, the shear stress is given by mu V p by h. Now, that is a positive quantity, and then according to our sign convention this is the stress element. Because it is positive, on a positive phase the direction of force is along the positive axis. In this case it is a positive y phase and force along positive x axis, and here it is positive x phase and force along positive y direction. So, because we are considering tau y x, force along positive x axis on a plane perpendicular to positive y axis, that is what we discussed just now. Okay. If your plane is the perpendicular to the plane is along positive y axis, force acts along positive x axis. Now, we will also interpret in this way, which I have not discussed so far, but intuitively we can understand that if we are considering this force, we are considering positive force, then that force is exerted by fluid in greater y on fluid in lesser y. What does it mean? You have fluid here and you have fluid here, and this force is exerted by this fluid on this fluid. That is what we mean by force exerted by, if you this is the y axis, okay, this is the y axis, okay, and so this liquid is in greater y, this is in lesser y. So, this force exerted by fluid in greater y on fluid in lesser y. Of course, we have seen this several times, but we can look this in this way also. Okay. And why is that? The fluid here flows at a higher velocity compared to fluid at a lower y, and hence the fluid in the top region exerts force in the positive direction on the fluid in the lower region. Okay. Okay. Now, what we will consider is once again a planar cuvette flow, but now with the top plate fixed and the bottom plate kept moving at a constant velocity Vp. Okay. This is the example which we are going to discuss to relate fluid mechanics and momentum transport. We will understand why we have come from that geometry to this geometry as we go along. Okay. Okay, let us look at that. So, flow between two parallel plates, top plate is stationary, the bottom plate moves at a constant velocity Vp. Now, what is the velocity profile? If we go through the derivation, if we go through the same procedure as we have followed earlier for deriving the velocity profile for planar cuvette flow, for this case what is that? The velocity is 0 here and the velocity is Vp here, and solve the Navier-Stokes equation, you will get this velocity profile Vx is equal to Vp into 1 minus y by h. But we can quickly check whether it is right. At y equal to 0, that is at the bottom plate the velocity is Vp, and y equal to h, this becomes 0 and the velocity at the top plate is 0. Okay. Okay. Now, if you find the shear stress tau x, okay, I use a subscript Fm meaning fluid mechanics, we will understand that as we go along. What is the shear stress expression? It is mu dou Vx by dou y. Now, if you differentiate the velocity profile, you will get minus Vp by h, and so the shear stress is minus mu Vp by h. According to our sign convention, if you want to represent a shear stress component which is negative, then on a positive plane the force should be along the negative axis. So, in this case is a positive y plane, force is along the negative x axis. Okay. Similarly, other forces are shown here. Okay. And if you look at the bottom face, the normal to this face is along the negative y axis, so the force is along the positive x axis. Okay. Okay. Now, so tau x is negative, the shear stress is negative. Now, once again we want to consider force along positive axis. So, let us take this force, and so now in this case the positive force will act on a plane whose perpendicular is towards the negative y axis, that is what we have seen here. Okay. Now, how do we interpret what is the equivalence of the last sentence in the previous slide for this case? Now, if you consider this force, okay, this exerted by fluid in lesser y on fluid in greater y. Why is it so? This fluid on the lower y or lesser y has a higher velocity and fluid at a greater y has a lower velocity. So, this fluid in this region tries to pull fluid in this region, hence this force is exerted by fluid in lesser y on fluid in greater y. Okay. Almost everything is opposite to the previous case. Okay. This is the case which we are going to discuss, or use this case, use this configuration to compare fluid mechanics and momentum transport. Okay. So, let us proceed further. Let us compare both the planar cuvette flow case, both of them are flow between parallel plates. Both of them are flow between two parallel plates. The first case which I have been discussing so far, the bottom plate is stationary, top plate moves at a constant velocity Vp. in the let us say new planar cuvette flow, top plate is stationary, bottom plate moves at a constant velocity Vp. What is the velocity profile? It is Vp by h into y, and now the velocity profile is Vp into 1 minus y by h. What about shear stress? Tau x is equal to mu Vp by h, and the present case tau x is equal to minus mu Vp by h. And the first case tau x is positive, second case tau x is negative. And if you consider a positive force along x axis that acts on a plane whose perpendicular is towards positive y axis. The second case, the new case, if you consider a force along positive x axis that will act on a plane whose perpendicular is towards negative y axis. The first case, force exerted by fluid in greater y on fluid in lesser y, and the present case, force exerted by fluid in lesser y on fluid in greater y, okay. And we are going to focus on the case on the right hand side. Okay. Now, what is that we are going to do now is give a molecular interpretation for tau. Okay. So, as I told you, we are going to take the case where the bottom plate is moving, top plate is fixed. Okay. Flow between two parallel plates, the top plate is stationary, bottom plate moves at a constant velocity Vp. Now, what happens? This bottom plate has some momentum, okay, and the fluid moving near this plate acquires some momentum from this plate, okay, and that imparts to the fluid above that. Okay. So, fluid near the plate acquires some momentum and then imparts to the fluid which is above that, and so this fluid which is near the plate imparts some of its x momentum, we are talking about x momentum here, to adjacent layer, causing it to remain in motion in x direction. Okay. At the molecular level, what happens is that generally molecules move in a random motion, but now the molecules will have a higher x velocity, let us say in this plane, and the molecules in this plane will have a lower x velocity. Overall the molecules have two components, one is the random component, other is the x component. The molecules in this layer will have higher x velocity, hence higher x momentum, and molecules in this layer will have lower x velocity and hence lower x momentum. And now let us say molecules move from this layer to this layer, they carry with them the higher momentum, and then when they reach the top layer, they transfer their higher momentum to the molecules in that region. That is why here we use the word due to molecular motion. Let us read the sentence again. This fluid, so when you say fluid, think in terms of molecules in that region. This fluid in turn imparts some of its x momentum to adjacent layer, causing it to remain in motion x direction. Okay. So, what happens, how do you interpret this? So, molecular x momentum is transported through the fluid in y direction. Look at the word here very specifically, we have used molecular x momentum, and that is x momentum, but is transported through the fluid in the y direction, more specifically in the positive y direction. Okay. So, plate has some momentum and the fluid moving near the plate acquires some x momentum, and that imparts x momentum the next layer of fluid. And in terms of molecular picture, molecules have a higher x velocity here and higher x momentum, and when they move to this layer they carry with them higher x momentum, which means that they transport x momentum in the y direction. Now, one like to distinguish this molecular x momentum with our usual momentum which we have been discussing so far. Okay. Our usual momentum, we say momentum in and momentum out, this picture has to be kept in mind, that we have discussed several times. So, if you take a control volume, we say momentum entering, momentum leaving, etc. This is by bulk flow, which we call as convective X momentum. Okay. In this present case, in the y direction, remember there is no convection, there is no flow in the bulk flow in the y direction, you have bulk flow only in the x direction. So, x momentum gets transported in the y direction because of molecular motion, and hence this momentum is called as molecular x momentum, in contrast to the our usual convective momentum, which is because of bulk flow. So, this has to be kept in mind as we go along. So far we have been using just x momentum, meaning it is convective x momentum, but right now we have two different forms in which momentum is transported, two different forms of momentum being transported. One is molecular x momentum, other is convective x momentum. Okay. Now, how do we interpret tau? How do we relate this tau to this momentum transported? Okay. Now, in momentum transport, what do I mean by that? In the momentum transport approach of analyzing fluid flow, one is the fluid mechanics way of analyzing fluid flow. Now, the momentum transport way of analyzing fluid flow, we have talked about this transport of x momentum in the y direction, the rate of molecular x momentum transport in y direction per unit area. What is area? In this case, you have two plates. So, the area through which this transport takes place, and of course, perpendicular to y axis is interpreted as molecular momentum flux. So, this is interpreted as the molecular momentum flux. What is the nomenclature? Tau yx momentum transport. Is it okay? That is why previously we used tau yx subscript fluid mechanics. Both are tau yx. So, just to distinguish, earlier we used subscript fluid mechanics, now we are using subscript momentum transfer. Okay, let us read it again. What is that we are doing now? We in the few minutes back we discussed about x momentum being transported in a y direction. Now, we are trying to quantify it or express that as a flux. So, rate at which that molecular x momentum is transported in y direction and per unit area perpendicular to y axis, means several terms are there here. One is rate, molecular x momentum, and then in y direction and per unit area perpendicular to y axis. Okay. And that is interpreted as the molecular momentum flux tau x momentum t. Okay. And now, it is clear that if the velocity gradient is higher, what does it mean? In this case, anyway, this velocity is 0, let us say this velocity is higher and higher, then the velocity gradient is higher and the molecular flux will be more, higher will be the molecular flux. Okay. So, the molecular x momentum flux is proportional to the velocity gradient. This is based on intuition that the x momentum being transported in y direction will be more if the velocity gradient is more. So, molecular x momentum flux is proportional to the velocity gradient in terms of an expression tau x momentum transport proportional to the velocity gradient. What is the velocity gradient here? Dou Vx by dou y, and the proportionality constant is the viscosity, and so we write the tau x in momentum transport as molecular momentum flux proportional to the velocity gradient with the proportionality constant as the fluid viscosity. Now, let us proceed further. We have seen this just now. In momentum transport, tau x is interpreted as the flux of molecular momentum. I have written the word flow because tau x is considered something flowing. What is it something flowing? That is x momentum being transported. So, flux is a more formal word, but in terms of understanding, in terms of imagination, it is a flow of molecular momentum. Okay. So, flux is a more formal representation of tau x. When we say flow, it says gives a physical meaning that molecular momentum flows, okay. And that is what is represented by tau x. Now, based on the discussion what we had, this molecular momentum flows from a region of higher velocity to a region of lower velocity, that is very obvious based on our discussion earlier. So, x momentum, molecular x momentum flows from a region of higher velocity to a region of lower velocity, which means that it is along the direction of negative velocity gradient. Velocity decreases in this direction and the momentum flux is also in that direction. The direction in which x momentum is transported is also along the direction in which velocity decreases. Now, we will adopt a sign convention, okay. That is the key in fact. We will adopt a sign convention. What is the sign convention? I want my molecular momentum flux to be positive along the positive y direction. So, I want this flux to be positive. Remember, this flux is along the positive y axis. I want this flux to be positive along the positive y axis. How do we do that? In the previous slide, we have written tau x is equal to mu dou V x by dou y. Suppose if I stop at this, what will happen? For the present case, dou V x by dou y is negative, and hence I will have a case where I have a negative momentum flux flowing along a positive y axis, which is little counterintuitive, because whenever we have a flow, we want that to be positive along a positive axis. For example, let us say we have velocity. When I say positive velocity, I want the flow to be along positive x axis. I do not want to be against I do not want the flow to be towards negative x axis. Similarly, here, because we have interpreted tau x as something as a momentum flowing, that is why this flow is written here. Whenever you imagine tau x for momentum transport, imagine as if something is flowing. What is that? X momentum is being transported in the y direction. I want that flow, that flux to be positive along positive y axis. How do you take care of that? By including a negative sign. Now, what happens? Dou V x, for this case, dou V x by dou y is negative and you have another negative sign. So, now my molecular momentum flux becomes positive along positive y axis. That is why we include a negative sign, so that the flux is positive along positive y axis. Now, this is the reason why this example was considered rather than our usual example. What would have happened? In this case, I would have had a molecular momentum flux in the towards the negative y axis. I will have a negative molecular flux towards negative y axis, which is a little inconvenient to discuss. That is why we took this case where there is positive momentum flux towards positive y axis. Both result in same sign convention, negative momentum flux towards negative y axis. Right now we have positive momentum flux towards positive y axis. So, want to take a case where we deal with only positive y axis and positive momentum flux. That is why this example was taken, this cuvette flow was taken rather than this cuvette flow. Okay. So, what is tau x? Now we can understand the subscript also. Tau x is flux of molecular x momentum transported in positive y direction. That is a formal nomenclature for tau x. Okay. Of course, you can also say molecular flux of x momentum. What does it tell you? You have a molecular x momentum transported in y direction. The flux of that is the tau x. Okay. And now, just like we had in fluid mechanics, force exerted by a fluid in lesser region on a fluid in higher region, similar to that, what is the direction of transport? From a region of lesser y to a region of greater y. You have a region of lesser y to a region of greater y. Remember, we are talking about a positive tau x momentum transport value. So, when this is positive, these two are for a positive value of tau x momentum transport. If it is positive, then the flux of molecular x momentum is along the positive y direction, and then it flows from a region of lower y to a region of higher y, that is what is happening, from a region of lesser y to a region of greater y. Okay. Just to summarize this slide, the only addition in this slide compared to the previous slide is, the previous slide we interpreted tau x from a molecular momentum transport point of view. In the present slide what we have done is included a negative sign, that is the only addition in this slide. Why did we do that? Based on the sign convention that the molecular momentum flux should be positive along positive y direction. Okay. Based on that sign convention we have included this negative sign, and we also given a formal we also interpreted what a positive tau x momentum transport means.